Hey folks, so welcome back to part two of our latent heat lesson, and this one we're going to look at the latent heat and specific heat capacity in calculations. So let me just remind you of what we did in part one. We talked about substances changing phase, which meant they went from a solid to a liquid or back, or a liquid to a gas and back again. And that when a substance was changing state or undergoing a phase change, its temperature would stay the same, and that there was these quantities called a latent heat of fusion and a latent heat of vaporization. Now, just to remind you again, a latent heat of fusion is the energy needed for a substance to change from a solid to a liquid, and the latent heat of vaporization is the energy needed for a substance to change from a liquid and a gas. So make sure you are very clear on what these two quantities are. Now, here's the equation that we're going to focus on today, which is that for both types of latent heat, the equation is EH is equal to mLH. So EH is the heat energy, M is the mass, which is always in kilograms, and latent heat is in joules per kilogram. And you need to choose which latent heat based on which phase change is happening. So I'll show you this a bit later on. The second thing to note in this is that there is no change in temperature. And this is because a lot of pupils get confused about which equation do they use. Well, remember, if there's a change in state, there's no change in temperature, so there's no temperature change in the equation itself. And that's how you remember which one's which. Now, to show you what I'm talking about and to also remind you of what we did before, remember we had the specific heat capacity, which was the energy needed to raise the temperature of 1 kilogram of material by 1 degree Celsius, and it has units of joules per kilogram per degree Celsius. And notice that in the equation for this, we've got M, just like before, but we have C and a delta T. So remember, latent heat's no temperature change, specific heat, a temperature change. And remember that C works both ways. It's the same whether a subject or an object rather is heating up or cooling down. Now, to summarize and to show you clearly what I'm talking about, here's the two equations we're going to be using in the next couple of examples. And if there's one slide I would really want to write down and make notes on, it's this one here. So remember, this one is the latent heat, which we only use if there's a change in state. And remember, you have to choose which latent heat to use, whether it's the latent heat of fusion or the latent heat of vaporization. I forgot to mention to you as well that you'll always be expected to look up what these latent heats are from the data sheet. The second equation you'll be expected to use is the specific heat capacity. And remember here, there is a change in temperature. And again, remember the specific capacity, you can look it up in the data sheet. So remember, latent heat, change in phase, no temperature change, it all fits together. Specific heat, there is a temperature change, so that's why there's a delta T there. Now, just like other calculations that we've done before, this is the routine that I want you to try and learn. And if you learn this routine, you'll be able to do these questions fairly easily. So there are usually two parts to these questions. Work out the energy needed to change state, i.e. EH is equal to mLH. Work out the energy needed to change temperature. Use EH is equal to Cm delta T. And then usually you might be asked to add the two together. So let's see if we can use this routine to answer some worked examples. So here's a typical question. A kettle holds 0.25 kilograms of water. It takes a time of 1 minute to heat the water from 22 degrees Celsius until it's boiling. Pause the video and have a wee look at the other questions. I'm going to take you through each of these step by step. So for the very first question, it says, calculate how much energy was needed to heat the water to boiling. So first of all, I've given you the latent heat of fusion and vaporization for water, and also the specific heat capacity for water as well. Now, we can use our KFC technique here. This is kind of like the KFC technique, and it says how much energy needed was to heat the water to boiling. So the first thing It's assuming you know that boiling water is 100 degrees Celsius. The second thing is, because it's changing temperature from 22 to 100, that means we have to calculate the change in temperature. So again, you've done this before. Now, if there's a change in temperature, which equation do we use? Hopefully you can tell me it is EH is equal to Cm delta T. Because once you have that down, the rest of it is just straightforward. So this is the know it part, the find it is the equation, and then calculate it. You plug in your numbers, you make sure you put the units at the end. Now notice as well that the time here is actually a red herring. We don't need to use this at all. Part 2 and 3, 2 it says, state what happens to the temperature of the water when it's boiling. Well again, hopefully you can tell me that when it's boiling, there's a change in state, so therefore the temperature stays the same at 100 degrees Celsius. Now, calculate how much energy was needed to turn the water to steam. So here, it's a phase change, so the equation we're using is EH is equal to mLH. Now the question is, which one of these do we use? Do we use fusion or vaporization? Well, remember, it's changing from a liquid to a gas, so it's going from a liquid into a vapor, so it's latent heat or vaporization. And once you've found all these bits, you're then onto the final stage of a KFC, you calculate it. So there you can see you plug in your numbers and we get the answer, and remember units in joules. Final part of the question, it says, state how much energy was needed in total to turn the water into steam completely. So that's given by total energy is the energy to change temperature plus the energy to change state. And so we add our two answers together and we get this as a final answer. So review the routine, folks. Look at how we did each stage and see if you can reproduce that when you do the next example. Okay, so example 2, a 5.5 kilogram lump of iron enters the Earth's atmosphere. It melts into a liquid with a temperature from 120 degrees Celsius to 320 degrees Celsius. Calculate the total energy needed to do this. And I've given you the latent heat of fusion, vaporization, and the specific capacity of iron. Now, have a go at this one yourself. Notice how it goes straight to calculate the total energy needed to do this. Pause the video, have a go of it, and then I'll show you how to do it over the next couple of slides. Now, notice in this example here, it doesn't take us through the calculation step by step like before. It doesn't ask us to do the change in state and then the specific heat one. We have to figure this out for ourselves. And hopefully you realize that because first of all, you can see it starts as a lump of iron, so you assume it's a solid, and then it even says it melts, so it melts into a liquid. And then the other thing as well is that there is a change in temperature. Now, it doesn't matter whether you do the latent heat first, because there's a change in state, and then do the specific capacity, because there's a change in temperature. You're going to have to do both, so it doesn't really matter which one you do first. So I'm going to do the latent heat because it does say it melts first of all. So EH is equal to mLH, and normally you'd be expected to look this up yourself, but I've provided it for you, and it's just our KFC technique now. So we know it, find the equation, and then calculate it. So plug in our numbers. Now remember, our mass is in 5.5 kilograms, and the units are correct. So we can just plug it in, and then we get this as our answer for the heat energy required. Now to do the change in temperature bit, we do the same technique, KFC. We know it, find the equation, and then calculate it. And notice how I'm using the C here. The mass is still 5.5, and the change in temperature was 200 degrees Celsius. And that gives us the energy required to change that temperature. And then finally, to get the total energy, we just simply do the sum of these two, which gives this as a final answer. And remember, your unit's joules. Again, the thing I want you to notice is we've used the same routine as before. Calculate a latent heat energy, calculate a specific heat energy, add them together to give us the total energy. Look for keywords like melts, freezes, condenses, or evaporates, and that will tell you which latent heat is happening. And if there's a change in temperature, you look for that as well. Okay, hopefully that's been useful. Have a go at the questions.